So good afternoon, everyone. Welcome back to Math 122. The notes are updated on Blackboard if you want to download the blank notes for this chapter. So today we're going to continue our discussion of Chapter 5, and then we're going to have a quiz. So regarding homework, you have one homework assignment, which is going to be due on Wednesday of next week. And I think I'm going to post one other homework that'll be due on probably Friday of next week or something like that, or maybe Thursday, on the first part of Chapter 5. So your next assessment is Quiz 8. That's today, but I'm going to delete this because I also want to let you know about the second exam, which is going to be your next assessment after that. Exam 2 will be on April 11th, which is a Tuesday. So we're going to have the review on the Thursday before. So 1 week from today, we'll have the review in class. So no quiz next week. The content for Exam 2 will be, well, where did we stop for Exam 1? That's a question. So that would have been Chapter 2. Here we go. Let's see if we can find that. No? Still gotta go further back. We better get this sorted out. Here we go. So Exam 1 went up to 2.1. Okay, so Exam 2 is going to be sections 2.2 to 2.5, 3.1 to 3.4, and 4.1 to 4.4, and 5.1, let's say. So pretty big spread for the second exam. And I just want to reiterate a comment that I already made, which was that the average for the first exam was really high. So you guys did a great job on that. Very proud of you all. But I just want to warn you that the second exam is quite a big jump in difficulty. Now I think you all can do it, but I just don't want anyone to show up to the second exam and be like, oh shit, this is way harder than I thought it would be. So, Chapter 1 was all sort of review from other math classes for the most part. Chapter 2 was where we defined just kind of what is a derivative. Chapter 3 was how do we do derivatives. And Chapter 4 was how do we use derivatives to find mins and maxes, basically. That was Chapter 4. Okay, so all of that is going to be on the exam. There's going to be tangent line stuff on the exam, quotient rule, product rule, chain rule, min-max, critical points, first derivative test, second derivative test. It's kind of a lot of content. So just to remind you about the exam, all of the questions for the exam come directly from the homework assignments, okay? So these are the homework assignments that you'll want to study for the exam, and I will try to pull content relatively evenly from all of these homework assignments, okay? So probably, what do we have, like 4 sections from Chapter 2, 4 from Chapter 3, 4 from Chapter 4. Probably I'll do like a pretty even spread. The exam will be like 3-4 pages of problems evenly taken from each of these sections, okay? So probably there will just be like one question from Chapter 5 to do like a Riemann sum problem, okay? So are there any questions about the exam? Okay, let's talk about how you can study for the exam. There's my office hours next week, okay? So from 10 to 2 in the Math Tutoring Center on Tuesday, I'll be there. On Wednesday, my office hours are from 3 to 4 in my office up in LeConte 439. On Thursday, we will have the review in class, and I also have office hours from 11:30 to 1. And in addition to those, you can go to the Math Tutoring Center anytime from 10 a.m. to 4 p.m. Monday through Thursday, or 10 to 2 on Fridays. Highly recommend that you spend some time there going over some of these problems, because it may have been a while since you did some of those problems from Chapter 2 or early Chapter 3. You can also go to the SI sessions, so any SI, or you can go to Jacob's sessions, which Jacob will be doing a review session at some point, but do you have it scheduled yet? Probably not.
No, not yet, but there'll be an exam review session.
Okay, so it's not scheduled yet, but there will be a review session, a special one with Jacob before the exam. So really the best way to prepare for these exams is practicing those homework problems, right? Just put the homework problem on the paper in front of you, put all the notes away, and practice the problem. And if you can do it on your own without any outside help, then you're ready for that problem. And just move on to the next problem, okay? All right, so those are my tips for studying for the exam. Any questions? Oh, also, you need to make sure that you have the derivative rules memorized, okay? Because there's not really going to be, time to think like, oh, is the quotient rule this or is it that? Like, those have to be something that you can just sort of regurgitate immediately. So those derivative rules are probably a good thing to put on like a flashcard. So I would say do like 5 to 10 flashcards with all of your derivative rules, and also the formula for tangent line. You know, I've given you tangent line problems on like 4 quizzes now. There's gonna be a tangent line problem on the exam, I'm telling you. So you need to know the tangent line formula, so to be able to like just write it down. So those would be like the flashcards that I would make. And then maybe one for like the Riemann sum formula or something like that. Okay, are we on the same page about the exam? All right, cool. Then are there any other like administrative questions, comments, or concerns before we start in on content for today? All right, it doesn't seem like there are any, so let's talk about what we talked about last time. So actually, last time we started by finishing Chapter 4, which we finished Chapter 4 with this last section, 4.3, on global max and min. So the only difference between local max and min finding and global max and min finding is we also have to throw in the endpoints, right? We have to throw in the endpoints, and then we just make a table. And actually, we don't even have to do like first or second derivative test on our critical points, because we just know, look, the max and the min is either going to occur at one of the critical points or it's going to occur at one of the boundary points. So if you just list them all and find the biggest number, then you'll be able to find the global max on that interval, okay? So global max, we always couple with like a domain of, a specified domain where we're going to search for the global max in this region, okay? So that's the idea behind that. And then we moved on to Chapter 5, where we learned about this new thing where we're sort of saying, well, instead of having a function and asking about its rate of change, now I'm flipping the script. I'm going to give you the rate of change and ask you something about the function or the quantity itself, right? So if we have a certain rate of change for a certain amount of time, then what's the accumulated result, okay? So accumulated change. So the example we used here was that if you are traveling at a certain speed for a certain amount of time, then you can find out how far you traveled, right? So in this case, the rate of change is your speed, and the quantity is distance. So if you accumulate this rate of change over a given period of time, you can find out the total change in quantity by computing the area under the curve, okay? The area under the curve, which is easy when your curve is a line, especially if it's a constant line, because we know how to do the area of boxes. And The next hardest thing is doing the area of 2 boxes, and then the third hardest thing was, or I guess third more difficult thing, was doing the area of half a box, aka a triangle. And then we asked the question, well, what if our function is curvy? Then how do we figure out the area? And we said, well, we don't know yet, but we can approximate the area under this curve using rectangles. So if we use 2 rectangles, we get a picture which looks like this thing on the left. And there's a lot of missed stuff, right? There's stuff that we counted that we shouldn't have counted, and then there is stuff that we didn't count that we should have counted. And so this area of these 2 pink boxes is not going to be exactly the same as the area of the under the blue curve. But it will be pretty close. And we noticed that the more and more and more rectangles we use, the better and better and better the approximated area will get. Okay? It will get closer and closer and closer to the true area. Okay, so what we defined at the last part of class last time was how to actually compute these areas, and it comes in the form of this summation notation. So the summation notation just says, look, I goes from something to something. In this case, it goes from k to n. And then f of I is what you're going to do, and the sum means you're going to take each I value between k and n, and you're going to plug it into the function, and then you're going to add them all up. Right? So we get f of k plus f of k plus 1 plus f of k plus 2 all the way until we get to f of n minus 1 and then f of n, and we add them all up. So for the I equals 3 to 7 of I squared, we do 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. So we start with 3 because that's what's on the bottom, and we end with 7 because that's what's on the top. The rule here tells us what to do to each number, i.e. square it, and the sum tells you to add all that crap up. Okay, so that was summation notation. And the summation notation for a Riemann sum went like this. So for a left-hand sum, well, the first thing we do is we say, look, however many rectangles we have is going to determine how wide they are, right? So delta x is the width of each rectangle, which is given by just, look, the length of the interval divided by however many rectangles you have, right? So that can be seen here. If your interval goes from A to B, then in this case, n equals 4. So the width of a rectangle here would be b minus a over 4, right? Because you take the length, which is shown in red beneath this graph, and you divide it by 4 to get the width of each rectangle. So that's the width of each rectangle. And then you have to multiply, to get the area of the first box, you have to multiply that width times the height of the function on the left side of the interval, okay? So we use I equals, so we go I equals 0 to n minus 1 is going to give us f of a plus I times delta x. So I goes from 0 to n minus 1. So all of these inputs, okay, all of these inputs are going to be the x values here, 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 and here. And we don't go all the way to b because the last rectangle's height is whatever is the height of the function on the left side of the final interval. So we end at b minus delta x, or a plus 3 delta x, okay? So you count however many rectangles you have. So if I is 0 to n minus 1, then you have 0, 1, dot, 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 up to n minus 1. If you count up the number of rectangles, altogether, since you start with the first one being 0, the second one being 1, then n minus 1 will be the nth rectangle. Okay, so that's why we go from 0 to n minus 1 for a left-hand sum. So are there questions about this formula so far? Yeah, we're going to do examples in just a second. Okay, I want to show you one other way that it's written. This is the way that it's written in your textbook, which is really the same thing. They say it's the sum from I equals 0 to n minus 1 of delta x times f of xi. The only difference here is that they say xi is a plus I delta x. So in this case, you would have x0 here. You would have, why don't I use a different color? You would have x0 here, x1 here, x2 here, x3 here, and x4 there. So we're going to go from, so for this one, we would do I equals 0 to 3, okay? And we would use x0, x1, x2, and x3 as the inputs to get the height of each rectangle shown here. So that's a left-hand sum. Okay, for a right-hand sum, it's going to be similar, except we're going to do the sum not from I equals 0 to n minus 1. We're going to go from I equals 1 to n of delta x times f of a plus I times delta x, which of course is the same as the sum from I equals 1 to n of delta x times f of xi. So the difference here being that the height of each rectangle is taken to be the height of the function on the right side of each interval. So we use these heights to determine the height of the rectangle. So that's x1, x2, x3, x4. So we have 5 points. We need to use 4 of them. It's either the 4 on the left or the 4 on the right, which we're using for either a left-hand sum or a right-hand sum. Okay? So these are our formulas, which we're going to be using to approximate the area under a curve using n rectangles. So a stereotypical problem will look something like, here's a function, and it'll say like x cubed minus 9x. And it'll say, approximate the area under this function from 0 to 7 using 3 rectangles. And your job will be to fill in the details of this Riemann sum and then compute it. So are there any questions about the theory before we see some examples? All right, I'm going to do 2 examples, and then I will set you free to work in groups on this stuff, because it takes some time to get used to doing it. I want you to have some group work time today. So let's see some examples. I want to do the simplest possible example first, so I'm going to make one up. Let's do the area under f of x equals x squared from a equals 1 to b equals, let's do 5. Using 4 rectangles and a right hand Riemann sum. All right, so let's draw a picture of what we're trying to do here. So by now, we know what the function x squared looks like, right? Looks like a parabola, which I was really hoping it would straighten it out for me. Can you please straighten it out for me? There we go. And then we're going to move that to look correct. Oh, come on. Okay, good enough. So now what are we doing? So we want to find the area underneath this function from a equals 1 to b equals 5. So here's 1, 2, 3, 4, and 5. So what we're looking for at the end of the day is the area which is trapped between these two which is trapped in this orange box. Okay, that's the area that we want. Okay, that's the area. Are we all okay with the premise of the problem so far? Okay, so from the previous note box, we learned that A is approximately equal to, now we're going to write down this thing. So it's the sum from, and I'm doing a right-hand Riemann sum, so I'm going to use the formula for a right-hand Riemann sum, which says I should start with I equals 1 up to n. Okay? So I equals 1, and remember n is the number of rectangles. So they tell us that we have 4 rectangles, which tells us that n should be 4. So I'm going to go I equals 1 to 4. And now what needs to go in here is delta x times f of x plus I times delta x. Okay, and let me draw what that thing represents. Okay, what this represents. So maybe I'll use blue to detail what this actually is on this picture. Okay, so it's a right-hand Riemann sum. The first height that we choose is f of x. Oh, sorry, this should not be x. This should be a. Sorry about that. We need a here. A plus I times delta x. So the first point which we're going to use will be a plus, well, it will be when I is 1, so a plus delta x. So let's figure out what delta x is. Well, delta x is given by the formula b minus a over n. In other words, the width of each rectangle will be the entire length of this interval divided by however many rectangles you use. So in our case, that is 5 minus 1 over 4, which is 4 over 4, which is 1. So each rectangle should be 1 unit wide. And I'm going to use 4 rectangles, and each rectangle's height will be the height of the function on the right side of each subinterval. So when I say subinterval, I mean this is our first subinterval, this is our second subinterval, this is our third subinterval, and this is our fourth subinterval. So we're going to choose 4 rectangles whose height, the height of the first rectangle will be the height of the function on the right side of the first subinterval. So the right side of the first subinterval would be when x is 2. So that's going to be a rectangle which looks like shown. And you know what? Before I draw that, let me copy this. And after that, I'll show you what a left-hand sum looks like. So we take the height on the right side of this first subinterval to be the height of our first rectangle. Because we're only looking for the area in orange here. It says, the problem says the area underneath this curve from a equals 1 to b equals 5. So that's why we're not counting that first part from 0 to 1. Okay, so here's our interval, or here's our first rectangle. Then our second rectangle's height will be the height of the function on the right side of the second subinterval. So that's here. So up to there. And then we have a rectangle like shown. And then from 4, we go up to here. And then we make a rectangle. And then at 5, we use this point here to make our rectangle. Okay, so the idea is that the area which is encapsulated by this red highlight will be close to the area which is captured by the blue boxes. Okay, and this is a right-hand sum because we take the height of each rectangle to be taken from the right side of each subinterval. Okay, so let's see what that is. Well, all we have to do is take each term. Well, delta x is 1, so we do 1 times f of a is 1, and then initially we have I equals 1, right? So we're going to add 1, that's what I is, and then times delta x, which is again 1. Then plus delta x is again 1, but now I is 2. So this will be times f of 1 plus 2 times 1. Plus 1 times f of 1. And now I is 3. So now we do delta x is 1 again. A is 1 again. So but I now is 3. So we do plus 3 times delta x, which is the same as plus 3 times 1. And then plus, and the very last one we're going to do is when I is equal to 4. So we get 1 times f of 1 plus 4 times 1. So if we simplify this, what do we get? If we simplify this, we just get f of 2 plus f of 3 plus f of 4 plus f of 5, which, since the function f is x squared, we can plug all those numbers in and we get 4 plus 9 plus 16 plus 25, which I think is 54. So 54 is the combined area of these 4 blue boxes, because the first box's height is what you get when you plug 2 into the function. So this height here is 4, right? So this is 4. Why don't I do blue? So this is 4 units tall and 1 unit wide. This one is 1 unit wide and altogether 9 units tall. This one is 1 unit wide and altogether 16 units tall. And this one is 1 unit wide and 25 units tall. So the area of each box, since it's only 1 unit wide, it's just 1 times whatever is the height, right? So the area of these boxes goes 4, 9, 16, and 25. So if we add up all of those areas using this summation, we get the area of these blue boxes, which is something close to the area of the orange shape. All right, let's let that soak in for a second. How do we feel about that? Yeah, Braden.
So I'm confused with the left and the right hand side.
Okay.
Could you do the same problem with the left hand or no?
Yeah, you absolutely could. And that's what I was about to do.
Okay.
So let me show you what it would look like with a left-hand sum. Well, with a left-hand sum, we would just use this exact same formula. The only difference is that I, instead of going from 1 to 4, it goes from 0 to 3, which means that the heights of the boxes will be, instead of taking the height on the right side of the first subinterval, we're going to take our rectangle's height to be the height of the function on the left side of the first subinterval. So we'll get a picture which looks like the following. Okay? So let's take a look at the difference between these two. Which, what would we get, by the way? This one would have height 1, width 1. This one would have height 4, width 1. This one would have height 9, width 1. And this one would have height 16, width 1. So altogether, we would get for this one 1 plus 4 plus 9 plus 16, which is 25 plus 5, which is 30. So let's look at the difference between these two. You can see for this one we get an underestimate, right? So the difference between a left-hand sum and a right-hand sum is the choice of how tall do we make the rectangles. In the left-hand sum, we say the height of the rectangles will just be whatever is the height of the function on the left side of the subinterval. So you choose this to be the height, and you extend your rectangle to the right from the left. Okay, so you choose the height on the left. In the other one, you choose the height to be the height on the right. Yes? The height on the right. So that's the difference between a left-hand sum and a right-hand sum. Yeah, question?
Would you ever ask us to use both to get a closer approximation?
Exactly. So one thing you could do is take the left-hand sum, take the right-hand sum, and try to say, well, 30 is an underestimate and 54 is an overestimate, so maybe the actual area is somewhere in between, right? No, not maybe, it is somewhere in between. But for different functions, okay, it's not always true that the left-hand sum will be an underestimate and the right-hand sum will be an overestimate. Sometimes it'll be reversed, and sometimes you won't be able to tell. It just depends on the function that you have. But because this function's convex, by which I mean this function is concave up, if you have a concave up function, which is, well, actually it's not because it's concave up, it's because it's increasing. If you have an increasing function, then the left-hand sum will always be an underestimate. But if we had, say, done the shape of something on the left side, where the function's decreasing, the roles would be switched. Okay, any other questions about this? What do we think is the toughest part of this Riemann stuff so far? Or do you have a question, Alex? What's up?
No, it's not a question. It's not a question. Actually, I guess it is a question. What makes the right hand different from the left hand? What is the terminology have to do?
Well,
What makes the top one a right hand? What makes the bottom?
Sorry?
What makes the top one a right hand? What makes the bottom one a left hand?
Right, so it's how we choose the height of the rectangles. So in both cases, we go from 0 to 5, right?
Yeah.
And we use 4 rectangles. So the question is, are you going to take 2, 3, 4, and 5 and make those to be our inputs to get the height of the rectangles, yeah? Or are you going to choose 1, 2, 3, and 4 and cause those to be the heights of our rectangles, like shown? You see the difference?
Yeah.
So that's the difference. That's the difference heuristically between left-hand sum and right-hand sum. In terms of the formula, the difference between a left-hand sum and a right-hand sum is that for the left-hand sum we go from I equals 0 to n minus 1. For the right-hand sum we go from I equals 1 to n.
Why, so that makes sense, I get that, but why does the right hand go exceeding and the left hand does not?
So it won't always be that way. It just happens to be that way for this function. If you want to know why it's true for this function, it has to do with the fact that this function is increasing between 1 and 5. This function is increasing. So that's why it's an overestimate for the right-hand sum, overestimate for the right-hand sum and underestimate for the left-hand sum.
So is it always how many why doesn't the left hand have to exceed?
Well, the left hand would be an overestimate if we were to say try to estimate this area here. Then the left hand will be an overestimate. But I'm not asking you to be able to tell whether it's an overestimate or underestimate yet, okay? I just want to focus on how to do a right-hand sum and how to do a left-hand sum. We'll talk more about whether it's an over or underestimate later. What do we think about all of this stuff?
This formula's weird.
The formula's weird? Do other people feel similarly?
Yeah, can you just like show plugging in the numbers for the left hand, like into the equation for the left hand, like you did for the right hand?
Sure. So if we were to do that, here's what it would look like. So you're going to let I be 0 first. So this would be, delta x, remember, is 1. And a, remember, is 1. And delta x is, again, 1. So we would do 1 times f of a is 1. And then I'm going to add I, which is 0 first, times 1. And then 1 times f of 1 plus now I is going to be 1. So 1 times 1. And then we would have plus 1 times f of 1 plus 2 times 1. And then plus 1 times f of 1, plus 3 times 1. So your i's go from 0, and then 1, and then 2, and then 3, and you stop at 3 because the top says 3. Yeah.
The n is 1 is because it's the...
It's given in the problem. A equals 1 to B equals 5. So they'll say from something to something. The left hand part of the interval is always your A value. The right hand is always your B value. Any other questions? So in my experience, a lot of students that I've had in the past are basically allergic to this Riemann sum notation. Because they're like, holy crap, now there's even more letters than there were before. I've got I's, I've got N's, I've got this weird delta thing. And it all just looks like chaos. But this is just a way of writing down the process, which the process is very simple. You use a certain number of rectangles, all with equal width. So the width is sort of a foregone conclusion. It's just however long your interval is divided by however many rectangles you have. And then you just need to figure out, well, how tall am I going to make each rectangle? And it's either going to be the height of the rectangle on the left, or height of the function on the left side, or height of the function on the right side of each subinterval. Okay? Are we ready to try on our own now? It's okay. If you try and fail, then you learn. So let's do a problem. So yes, we'll work on this one. Yeah. Okay. So get into your groups. I'll be walking around to help. please don't feel bad if you have a hard time with this at first, okay? It takes time to get used to this stuff, but make sure you draw a picture. I promise you the picture will help you a lot, okay? So draw a picture, try to write down what it is that you're trying to do, and then try to either apply the formula, or if you're allergic to the formula, then try to use the principles. All right, and Jacob and I will walk around to help. You don't have to whisper. You can speak to one another at like a normal volume. Collaborate with your peers.
Yeah. So it's just like why yeah, I mean, it doesn't really. The drawing is just there more so you don't. Means that we have 4, 8, 12, 16. No.
Is it okay for age 0?
Absolutely. In fact, it should be. Right? Because what do they say? They say T is in hours since the start of a 20-hour period. So if we're trying to estimate the total change over the 20-hour period, then that means T goes from 0 to 20. So our A should of course be 0, and our B should be 20. So yes, totally okay for A to be 0.
Is A just asking like how far each bar is?
Essentially, it's asking you, well, in so many words, it's asking you what is delta x?
Yeah.
Right, what is the width of each rectangle? If you divide a 20...
Yeah, I got that. Okay. That's what I was making sure.
Yeah, and what should the endpoints of each subinterval be? That's what it's asking.
It's the last one.
Now we hit him with
Do you go all the way up to 5?
no.
That's 150.
I see.
This is just Three up, but it should otherwise So what are we trying to do? We're trying to go from 0 to 20 using intervals, 5 time intervals of equal length. So we want to make 5 jumps between 0 and 20, right? Exactly, you go by 4. Because A is 0, B is 20, and N, the number of rectangles, is 5. So 20 minus 0 is 5.
I'm getting there.
0 to 4.
A little bit special ed. Took me a very long time to realize
We want to make
how
we're doing
mathematics works as a whole. When I'm
So the
getting
height of
there,
the first rectangle should be this height. Got it. Yeah. Exactly. Got it. All right. What's up?
With the fourth floor. That must be negative
0. If it's a left-hand sum, it should be 0. Exactly. It's either 0 or 1. It's never negative. We'll just think of it as like 0 to the left and 1.
I
Okay. So, yes, you can go from 0 up to 5 minus 1. So 0 up to 4.
what did you get for your?
And now we need delta x, right? Which delta x should tell us, or delta t in this case, should tell us the width of each interval, right? If we're using 5 rectangles, and the length of our interval is how long?
You had like, but like for like your ending functions, you had like,
Well, yeah,
for
the length of our
like 4
entire interval is 20, which if we use 5 rectangles means each rectangle should be 4 units wide.
And then I mean it was like 4 times half of 8.
Yeah,
Okay.
yeah.
Yeah, I just make sure. Okay, 160.
That's good. What's your question?
10 intervals. I'm not writing all of that.
Keep working. I think you're on the right track.
Simple. I'm not writing all of that. It's too many writing. Plus. Too many is writing.
One is for, so we have 5 rectangles, right? We gotta decide how tall is that rectangle. So the way we decide is that the first sum is always going to be 0 to 4. Since we're doing a left-hand sum, we choose the height of this leftmost rectangle to be the height of the function on the leftmost part of this subinterval. So the leftmost part is at 0. So we take what is the height of the function when the x value is equal to 0, and we extend that over to be the height of the rectangle. Okay, 0. The second part, our next subinterval is the height, again, you see the height of the function, 0 to x size, so it's 0 of the function, and we extend that over that subinterval. Where this rectangle, we choose the height to be the height of the function on the right side.
Good student.
It goes down to 5 times another 0. Like so. So we use 1 equals 0, and then remember the number of rectangles in our case is 5. So we go from 0 to 5.
Okay.
Delta
There's no way
x
we calculate all
with
that.
the rectangle. We've already determined is 4.
Thank you.
Right? So we're going to 4 into delta
Thank
x, 4 into delta x, and we're going to let I go from 0 up to. And we just plug in those numbers. The function is what numbers is.
Yeah, because you don't.
Remember, we go from A to B.
B.
So A is where we start. So where we start. Zero.
Zero
So
for
A
a
is
12. Stop at 12.
Wait, stop at one for which one?
For A, like your A, what you're putting in for A. I.
Ended up 20 minus 0 divided by 1.
Yeah.
Wouldn't that be your delta?
And then we have 0 plus.
Oh, no, oh, I is just minus 0
I
delta.
is actually just 0 here. 1, 2.
Oh, yeah. Okay, cool.
Exactly. So what we're gonna do with the sum means what? Plug in 0, then add, plug in 1, then add, plug in 2, then add, plug in 3, then add, plug in 3 plus. Got it. I don't know.
Basically, we do is times two ones instead of equal 0. Yeah, I changed the delta x.
You plug.
So what we have to do is from here, plug in,
Just like,
Yeah.
blah, 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 so we'll look back.
4.2 is just E up. You take the second order. You see if it's a deflection point. I can remember 4.1, but 4.2 is going to be a lot cheaper.
Basically, just do the first term of the test and the second
This one's
Yeah.
3 plus 1.1. So I think we gotta do, so I think we gotta do 4 times 0 plus
3 and then second memorize or size.
So yes, correct. Plug in I equals 0, 1, 2, 3, 4.
I mean, I like to do
Plug in
something.
4, 6, that's like. This is 4 times 0, right?
Did you get like 16 plus 32 plus 48 plus
This one is 4 times f of a.
Yeah, so I added.
So on and so forth. So you just take those numbers, plug them into.
What do you do left-handed, right? If it's left-handed, you have to add
Yeah.
You have to do 0 and 1 and 0.
Yeah.
And what do you get for 0? Like when you plug it?
Get 4 times f4, which is, or no,
It would be
4 times 0. Oh yeah, no, I'm looking for like,
I have no idea what's going on.
At least my calculator.
Starts from 1, so it goes 1 times 0 plus
You're right, it's 160.
you were close.
0 3 times.
I feel like that would have been.
Yeah, I would accept
Yeah,
that.
because A is bigger from the get-go. Oh, shit. We gotta do this quick. All right, we'll talk about this example next time. So clear your desks, please.